right, how's everyone doing? You ready to get going here?
Yes.
Grab my notes. All right, so last time we were talking about geometric series, and we saw that with the geometric series, we can actually determine the convergence or divergence of a series. In fact, if it's a geometric series and it converges, we actually know what it adds up to be, which is really important. We were last class talking about there were three series that we were going to look at: geometric, harmonic, and telescopic or collapsing. So we've covered geometric, okay? And we should all be comfortable with the idea that the sum n equals 1 to infinity of AR to the n minus 1 will converge. This is geometric. It will converge if the absolute value of R is less than 1, then it converges to A over 1 minus R. That means that's what this series adds up to be. So with a geometric series, we can actually find the sum. We can find the sum, all right, if it converges, if it converges. If the absolute value of R is bigger than 1 or equal to 1, then it diverges. So the next thing we need to do is talk about harmonic series, then telescopic, and then we'll probably get into 8.3 today, okay? All right, any questions? The exam going okay? It's due tomorrow, yes? At what time did I say? I forgot. Was it 1? What time did I say? I forgot.
12:30.
12:30? Okay. Sounds about right. Okay, so we move on. Harmonic series. So I've got really good news about harmonic series. Real good news. You're going to like them. All right. First, let's take a look at what they look like. All right. So all harmonic series look like this: sum n equals 1 to infinity of a constant, I'm going to put C, over a linear expression in n. So a constant over a linear expression in n. Let me give you some specific examples. Sum n equals 1 to infinity of 1 over n. That is an example of a harmonic series. Do y'all see that we have a constant on top, right? 1 over n, and n is linear, right? N to the first power. Okay, let me give you some more examples. Sum n equals 1 to infinity of 5 over 2n plus 3. That's harmonic. Constant over linear, right? Constant over linear. If you have constant over quadratic, that is not harmonic, right? It's got to be constant over linear. And I can keep going with more examples. Well, here's the good news. All harmonic series diverge. All of them, okay? And what that means is that as you add these things up, right? Because remember, a series is a sum, right? So as you plug in 1 and then 2 and then 3 and then 4, and you start adding these things together, and you keep doing that forever, it becomes unbounded. It blows up. It becomes infinitely large. Now, it might take a while for it to happen, but it gets really, really big, all right? So that's good news. Now, I need to prove it to you, but I'm not going to give you a formal proof. I'm just going to give you a kind of like, does that make sense? Do you see how we could conclude that this diverges by looking at just one example, okay? And then once I show you that one example, we'll move on to the next series, the next type of series. So isn't this good? We don't have to run tests. We don't have to see if something's less than 1. We just have to see it's constant over linear, boom, harmonic, done, all right? So let's see why these diverge. So let's take that first example. Sum n equals 1 to infinity of 1 over n. this is equal to 1 plus a half plus a third plus a fourth. I'm going to write a lot of these out. Plus a fifth plus a sixth plus a seventh plus an eighth plus a ninth plus a tenth, plus a 1/11th, 12. I'm going to go out to 16. You'll see why in a minute. Plus dot, dot, dot. Okay, so that keeps going forever, right? All right, so now I'm just going to write some things down and you tell me whether or not you agree with this or not, all right? So do you agree that this sum that I just wrote down is less than, okay? I'm sorry, not less than, greater than. Greater than, so that sum is greater than 1 plus, okay, a half. So far they're the same, aren't they? 1, 1, half, half. Okay, now what I'm going to do is I'm going to look at these two right here. Those two right there. Now, which of these is bigger? 1/3 or 1/4?
1/3.
1/3, right? 1/3 is bigger than 1/4. So do you agree that if I did plus a fourth, this right here would be smaller than a third plus a fourth, wouldn't it? And so if this right here is bigger than these two added, then this inequality so far would hold, right? This is the same, but this here, right, that there is smaller. This is smaller than that, right? Which means that the top row should be bigger so far, yes? Okay, now what is 1/4 plus a fourth?
1/2.
A half, right? So this is really a half. Okay. All right, now what I'm going to do is I want you to look at the next, not the next two, I want you to look at the next 4. What is the smallest number in this list of numbers? What's the smallest one?
The eighth.
1/8.
The eighth. So do you agree that if I did plus an eighth plus an eighth plus an eighth plus an eighth, that these eighths added together would be smaller than these things added together, right? Because the 1/5 is bigger than that, the 1/6 is bigger than that, the 1/7 is bigger than that, and the 1/8, well, those are the same, right? So these 4 added should be bigger than these 4 added, right? And so those 4 together is really what?
1/2.
1/2 again, right? 4/8, that's 1/2. Oops, that's 1/2 again, right? Now, how many do you think I'm going to go out this time?
8.
2, then I went 4. What do you think?
6. Maybe.
6 and 8 are the most common responses, but let's look at this. If we go out 8, right? If we go out 8, what's the smallest number in this list?
1/16.
1/16. How many of them do I have here? 1, 2, 3, 4, 5, 6, 7. I have 8 of them, right? So if I did 1/16 plus 1/16 plus 1/16 plus 1/16 plus 1/16 plus 1/16 plus 1/16, let's see, 1, 2, 3, 4, 5, 6, 7, one more, 1/16, then each of these in purple are bigger than each of those, right? So that sum up there should still be bigger than this. But all of those together, that's 8/16, isn't it? And that's 1/2 again. And then what I would do is I would add the next how many together?
16.
The next 16 of them, right? And they would all be, if you went 16 down from here, you'd be at 1/32. So I'd basically be adding to this 1/32 plus 1/32, and I would add 16 of those up together. And I'd have 16 32nds, which would give me another half. Does that make sense? And so if I continue this forever, right, then really what I'm saying is that this original sum here, right, is bigger than 1 plus a half plus another half plus another half plus another half plus blah, 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 forever, right? But this right here, if you look at this, this will diverge. The reason this diverges is because the individual pieces, right? The individual numbers we're adding up are not getting smaller. They're not going to 0, right? They're actually headed to 1/2. And we know that whenever the terms, the numbers inside of a series, if those numbers don't go to 0, then the series diverges. And so we can conclude here that this thing, all this should be infinite, right? This whole thing should be infinite. And if our original series has to be bigger than infinity, well, then it must be infinity also. So it diverges. Right? Does that make sense? You go out the next 32, add them up. You go out after that, you go out the next 64. And then after that, you go out 128 and then 256, right? And you can keep doing that forever. And you're just going up by powers of 2 each time. Okay, so I hope that that convinces you that harmonic series diverge. And let's see here. I think I can show this to you. Where is it? We looked at this last time, didn't we? Where we had the, whoa. Got something crazy going on here. Let me reevaluate this notebook. Okay, so the picture on the left is the sequence and the picture on the right is the series. So I'm going to just go 1 over n. We can see that the sequence, of course, drops down, right? 1, 1/2, 1/3, 1/4. But as I start to add them up, look what happens. All right, look at that sum. The sum keeps getting bigger and bigger. And as I go out, you know, eventually we're going to break past 5. And if I keep going, I should eventually break past 6. And if I keep going, I will break past 7. Does that make sense? And as long as this thing is linear or constant over linear, I can change that. Let me do 3 over 2n plus 4. There's another example. There we go. So you can see the same thing is happening. It just blows up. Now, what happens if I change that to like 1 over n squared? Right? That's not constant over linear. And I hope you can see from this illustration that this one looks like it converges, right? It's not getting bigger as we go out. I mean, it is getting bigger, but it doesn't seem to want to go past 2, no matter how far I go. So that's convergence, but that's not what we're looking at. I'm just trying to convince you that all harmonic series diverge. All right, can we take that and move on? Yeah. Okay. All right, let's move on to telescopic. So this last group that we're going to look at here, telescopic or collapsing series. Okay. These, if they converge, because sometimes they do, sometimes they don't. If they converge, we can find the sum. Now, this is important. Okay, this is important. Let me tell you why. No matter how many times I say this, students forget this when it comes to a test. On your final exam, if I tell you to find the sum of the series, okay, then that is telling you right away it's either geometric or telescopic, because those are the only 2 series we can find the sums of. That's the only 2. Everything else is just going to be a matter of does it converge or does it diverge. But if I tell you to find the sum, then I'm giving you a hint that it's either geometric or telescopic. I'm giving you that. So just be paying attention to that. Now, the word telescopic come and collapsing, the reason why we call these, the reason why they have that name, I can't explain to you until we go through a problem. Okay, let's work through a problem, and then once we work through the problem, you'll see why we call it telescopic or collapsing. Now, before we do an example, I want to remind you of something. Maybe I'll just go back in the notes. Yeah, let me go back in the notes because I think it'll be faster. We look at what we talked about last class. We said, look, if we're given a sequence, right, not a series, if we're given a sequence of numbers, then we can start adding them up, and we create these things called partial sums. So we could call S sub 1 just the first number, S sub 2 is the first 2 added up, S3 would be the first 3 added up, S4 would be the first 4, S7 would be the first 7, S sub n would be adding up the first n, right? We call these partial sums. And then we said, oh, look, this right here, this is a new list of numbers. And so we would like to know whether or not this converges or diverges, because now we've created a new sequence. So at the end of it all, we said, if we can find a formula for S sub n, if we have a formula for it, then all we need to do is take the limit as n goes to infinity of that. If that limit exists, then that S that we get, that limit, is the sum of the series. So just remember that, because we're about to do this. We're about to find a formula S sub n. We're going to take its limit and we're going to get an answer, and that answer is going to represent the sum of all of these forever, the infinite series. Okay, so let's start with our first example here of a telescopic. So we're going to do sum n equals 1 to infinity of 1 over n times n plus 1. Give me just a minute. I'm going to bring up something. I want to open up my notes on a different page. Nope, wrong day. That should do it. Where is it? Where is it? Oh. There it is. Okay. There we go. All right. So here it is. So let's just do the first thing. Is this geometric? Or you know what? Maybe we should do this. Let's run through our tests. What tests do we have? So we talked about this sheet last time, didn't we? A little bit. Okay, we have on the sheet geometric series. We have the whole kind of process here. If we see this, then it'll converge to a over 1 minus r as long as the absolute value of r is less than 1, and diverges otherwise. Now, what about this first test, the nth term test? What does this nth term test tell us? So why don't we get people involved here today? How about Alex? Alex Pohl. How you doing, Alex? Can you see this okay, Alex?
Yes, sir.
Okay. So the nth term test, the way this reads is that, okay, we're given a series, right? It says that this series will diverge if what? Limit as n goes to infinity of this piece right here, that's the sequence, right? The sequence. If the sequence goes to something other than 0, this series will diverge. What happens if the sequence goes to 0? What does this test tell us?
It reads that it's inconclusive.
Inconclusive, which means the test doesn't work. I'll illustrate this more, all right? So right here, if I look at the sequence, Alex, what part of this is the sequence? What's A sub n here for us, Alex? Just take a shot.
Would it be the lower half of it?
Okay, so the n plus 1, that thing?
Yeah.
Okay, that's part of it. Look, the whole thing, everything in here, okay, that whole thing is always A sub n. That's the thing we're adding up, right? We're adding those pieces up. So when you look at a series, whatever's in here is your A sub n, all right? Let's do this nth term test, Alex. Let's take the limit as n goes to infinity on this. And Alex, what does that go to? If n goes to infinity, what is that limit?
Would it just be 0?
0, right? Everyone agree? This goes to 0 because the top is fixed, the bottom gets bigger, right? So when this happens, right, when the sequence part of the series goes to 0, the nth term test tells us that you don't know anything, okay? It tells us that this test failed. Now, if it went to something other than 0, then we would say it diverges. So let me just illustrate that before we go too much further. So I want to do this problem, but I want to just do this on a separate page. What if we had this? Look at that series, okay? If we did the nth term test on this, then we would take the limit of the sequence. And in this case, that'd be n plus 1 over n plus 2. And here we have infinity over infinity. We could do L'Hopital, right? And we would figure out eventually that this goes to 1. And 1 is not 0, right? 1 is not 0. And according to the formula sheet, the nth term test says, hey, look, if you take the limit of the sequence and you get something other than 0, then the series diverges. And so we would be done at this point. We would just go back here and be like, oh, okay, this diverges. And we're done, all right? That's nice. The nth term test is nice, but it only tests for divergence. Students will make this mistake. They will say, all right, look, I take this, I take the limit, I get 0. And so 0 means convergence. No, that's not what it means at all, okay? 0 means this test fails. Is that clear, everyone? This right here, nth term test. Did I bring up the pregnancy test to y'all? I don't think I did, right?
No,
So
I don't remember.
I look at the nth term test as like a pregnancy test, okay? So, and please don't get offended because I'm talking about pregnancy test, okay? I think we can, I hope y'all can handle it. So the way pregnancy tests work is they usually have a little window. And then what happens is you take the test and what'll happen is there are 2 possible lines that could show up. There's a line here and a line here. So I think most of them are like, okay, if the first line shows up, then the test is working. And if the second test line shows up, that means you're pregnant. Okay. So this test, the nth term test, is kind of like a pregnancy test, where if the limit goes to something other than 0, you're pregnant. Okay. You're pregnant. You've got both lines. All right. It diverges, you've drawn a conclusion, all right? Now, if your limit goes to 0, it would be like this. It would be like this happened. What would you do if you had a pregnancy test that looked like this?
Assume it's not working.
Yeah, it's a broken test because do you trust that you're pregnant? Well, you needed both lines, right? The first line is to show that the test is working properly. The second line is there to show you whether or not you're pregnant. If you get this result, you better go get a new test, right? Because it looks, you can't draw a conclusion from this. Could you still be pregnant? Sure. Could you not be pregnant? Sure. Right? So when you do an nth term test and you get 0, your test is broken. You need a new test, okay? You cannot conclude that it's convergent or divergent. Does that make sense? Okay. So with this test on this collapsing series, the first thing we always want to do with any series is run this nth term test. If we get lucky, we'll get something other than 0 and we'll be done. Okay? But most of the time, you're going to get 0, which means you need something else. So the next thing I would do is I'd look at this and I'd be like, okay, is it geometric? Well, geometric means we need it to look like this. Geometric would mean we need sum n equals 1 to infinity of AR to the n minus 1. Does this look geometric to you? No, because for geometric, the n, right, is up in the exponent. And here, we don't have any exponents like that, right? So we can throw this out. No, it's not geometric, okay? So what's the next thing we've learned about? We just did. Harmonic, right? So this was geometric. Okay, is it harmonic? Is this harmonic? Do you have a constant over a linear expression? Well, if you multiplied out the bottom, it would be quadratic, wouldn't it? So this is a constant over a quadratic. So this is not harmonic. Okay. So that means we're at a dead end. Okay, so I have to now try and figure out what's going on here. Does everyone understand kind of like the big picture here? We've got a series. We want to start running through these tests to figure out whether or not it converges or diverges. The first test we always like to run is the nth term test. Maybe we'll get lucky. Then we just look, is it geometric, right? Now harmonic is not even on here. They don't even put harmonic on here because, well, it's here. It's actually part of this P series, but we'll get to that later. All right. So what next? What next? Well, one thing we could do whenever you kind of get stuck is start writing it out. Okay, so let's start writing this series out. I'm going to come down here because I'm kind of running out of room. Sum 1 over n times n plus 1, n equals 1 to infinity. Let's just start writing out what this is. If we plug in 1 here, what would we get? You get 1 over, wouldn't it be 2? Right, 1 times 1 plus 1. Or sorry, yeah, 1 times 1 plus 1, that's 1 times 2 is 2, right? We get 1/2. What would be the next one? So plug in 2 here, you should get 1/6. Plug in 3 there, you should get 1/12. Plug in 4 there, you should get 1/20. 5 goes in now, 5 times 6, 30, I believe that's right. And then 6 times 7, 1 over 42. Right, do y'all see that? The question is, does this converge or diverge, right? All right, well, so, I mean, when you look at this, there's really not much we can do. I mean, we're just looking at it going, yeah, there it is, right? So how do we address this? All right, so I'm gonna just ask you to think about this and think, have we seen something like that before somewhere in this class and done something to it? Give you a hint. If we had an integral that kind of looked like that, how would we attack that? We have distinct linear roots there, or distinct linear factors. How would we go about that?
Partial fractions?
Fractions, okay. So right now what we're gonna do, we're not integrating, okay? We're not doing any integration. I don't want you to think we're about to integrate. What we're gonna do is we're gonna say, hey, look, this we could do with partial fractions, couldn't we? I mean, like we could, if we wanted to on the side here, do partial fraction decomposition on 1 over n plus n times n plus 1. We could break that into a over n plus b over n plus 1, couldn't we? We could do that. That's just algebra. And if we do that, I'm not going to go through the work, okay? I'm going to trust everyone could do this. We would find out that this turns into 1 over n minus 1 over n plus 1. Well, that negative is up here on that. The negative turns out to be the b. It turns out to be -1, but I'm just going to put the negative out here. Okay? Now, why is this going to be good? Is that all right that I not show that work? Is everyone okay that you could do that?
Yes, sir.
Okay. So now let's take a look at what we're saying. What we're saying is that this sum is the same as the sum n equals 1 to infinity of not that expression, but 1 over n minus 1 over n plus 1. Okay? That's just algebra from here to here. Now, when you look at this, you might be very tempted at this point to do this. Do not do it, but I'm going to write it down. You might wonder, can this just become sum n equals 1 to infinity of 1 over n minus the sum n equals 1 to infinity of 1 over n plus 1? Does that seem logical that we might be able to do this? To take this and break it into two sums like that? Does that seem logical? I mean, yeah.
If you're thinking like it's integrals and not really sums.
Yeah, I mean, this happens with integrals, doesn't it? If we have an integral where we have subtraction, we can break it into two integrals, right? But aren't integrals sums? Isn't that really what an integral is? It's just a sum. So this looks like this would be okay, right? It turns out that it's not. And I have to give you a theorem before we continue, all right? But I didn't want to give you the theorem until I showed you why we would need it. So here's a little step to the side. We have a theorem that says this. It says that the sum n equals 1 to infinity of some sequence a sub n plus or minus some other sequence b sub n, it says that that is equal to splitting up the sums. So you are allowed to split the sums up. Only if both of them individually converge. So what I'm saying is this: you're allowed to split this up into two separate series with addition or subtraction between them, but you can only do that if these guys right here converge. If one of these diverge, then you're not allowed to split them up. Okay? You can't pull them apart unless they both converge. I'll give you a specific example of this underneath this. Let's say we had this sum n equals 1 to infinity of 2/3 to the n minus 4/5 to the n minus 1. All right, can we split those up? What do you think? Let me see. Is Jane here? Jane?
Yeah.
Hey, Jane. So what do you think? You think we can split this up or not?
Yeah, I mean, I would think so, since they're
Since what? Look at these individually. Can you tell me what type of series these are?
under the harmonic, no, close to the harmonic one, kind of.
This,
No.
okay. Does this look like a constant over linear? Where's the power? Where's the exponent? Look at that. That's your n, right? It's up in the exponent.
Yeah, it'd be the geometric one.
Yeah, these are both geometric, aren't they?
Mhm.
Now, even though this one here is not n minus 1, we could make it a minus 1, couldn't we? We could do like minus 1 plus 1.
Mhm.
Would that converge, Jane, or not? Would this first one converge or diverge? Do you know what the r is? Do you know the thing that's being raised to the power?
I would say,
2/3, right?
yeah.
Is that smaller than 1?
I would say yes.
Yeah. So this is smaller than 1. So this is a geometric series that should converge, right?
Mhm.
And this one is also a geometric series that should converge. So if both of these converge, then me splitting it up was okay. All right, that's okay to do. Now, had I changed the problem, thank you, Jane. Had I changed the problem to 3/2 to the n minus 4/5 to the n minus 1, had I done that instead, could I split it up? No, why not, Ross? I see you shaking your head there.
Because 3/2 is bigger than 1.
Yeah, that right there, even though it's geometric, 3/2 is bigger than 1, so it's going to diverge. So if you split it, you'll have one of the two will diverge, and that's no good. So you're not allowed to split it. Okay? Now, let's get back to the problem that we were looking at here. The question was, can I split this up into 2? No, right? Because this right here is harmonic, and this right here is harmonic, right? Constant over linear, constant over linear. These diverge, so me splitting it's not allowed. Okay, can't do that. So we're stuck with this. We just have to keep working with this, all right? So let's see now what the value of doing the partial fractions was, because you might be sitting there going, why in the hell are we doing this if it's not even gonna allow us to split it up? Watch this. Let's plug in 1. Let's just start writing it out. Let's plug in 1. What would I get if I plug in 1? I'm gonna write kind of small here. I get 1/1, that's 1 minus 1/2, 1/2. Wouldn't that be the first thing I get when I plug in 1? Okay, plus now the next one, I'm plugging in 2 for n. So I get 1/2 minus 1/3. And then the next one will be 1/3 minus 1/4. And the next one will be 1/4 minus 1/5. You see what's happening? Does anyone see a pattern here? Something good that's happening if I do this? Does anyone see it?
You can start to cancel out some of them. Like for instance, -1/2 plus 1/2 is just 0. -1/3 plus 1/3 is 0. -1/4 plus 1/4 is 0, etc.
Do y'all see that? There's stuff going away. A significant amount of stuff is going away, isn't it? All right, so now what we need to do, I know that you're going to be very tempted right now to just be like, oh, well, the only thing that didn't cancel is 1, right? So the answer must be 1. I know that's very tempting to do, but that is not what we're going to do, all right? In fact, if you do that on a test, that's going to cost you a significant amount of points on the test. Because all we've done up to this point is discovered that if we do partial fractions, we now have cancellation happening, right? There's something good happening finally. And so what we're going to do now is see if we can't figure out a formula for S sub n. So remember what I said. I said what we're going to do is we're going to go back to last class and we're going to try and come up with the formula for S sub n, and then we're going to take its limit. If that limit exists, that's what this series converges to. So let's try and figure out the formula for S sub n. So here's what it would be. It would be this sum, right? It would be this right here, but I actually stop at n, like I stop somewhere, right? So what I'm going to do is I'm going to rewrite. If I plugged in 1, just follow me through this first one. If I plug in 1, I get this. If I plug in 2, I get this. If I plug in 3, I get this. If I plug in 4, I get this. And then I'm going to keep doing that, right? Dot, 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 dot. And then I get to my very last one, right? But I'm stopping where? At n, right? That's gonna be the last thing I plug in. So watch what I do here. Way here at the end, I'm gonna show you what would happen if I plug in n. So here's what happens when I plug in 1. Here's what happens when I plug in 2. Here's what happens when I plug in 3. What would happen if I plug n into this formula? Well, we just get that formula, don't we? Right? We just get 1 over n minus 1 over n plus 1. Is that clear? Now, very important. What would the one right in front of that one be? So what am I plugging into this one? I'm not plugging in n. N is the last one. What would be the one right before n? What am I plugging in?
Is it 1 over n minus 1 minus 1 over n?
Yeah, so I'm plugging in this time n minus 1. Whatever this number is, 1 less than it. So plug n minus 1 into this formula. You'll get 1 over n minus 1 minus 1 over n minus 1 plus 1, which gives you just 1 over n. Does everyone see that? I'm taking I'm taking n minus 1 and I'm plugging it in there for n and there for n into the original formula. 1 over n minus 1, and then the other one will become 1 over n minus 1 plus 1, that's 1 over n. Let's go one more back, okay? Let's do the one right in front of that one. So this time I'm not plugging in n minus 1, I'm plugging in n minus 2. So if I plug n minus 2 into that formula, I get 1 over n minus 2 minus 1 over n minus 2 plus 1 will be minus 1. Are there any questions from anyone about what I just wrote out there and why I wrote it? Is that clear to everyone? This right here represents what we call the nth partial sum. No questions? We want to know what happens to that as n goes to infinity, right? We're going to take the limit of that, but let's do all our cancellation here. Varun said that -1/2 cancels with a half, -1/3 cancels with a third, -1/4 cancels with a fourth. How about this -1/5? Would it go away? Yeah, this would cancel with something here in that ... wouldn't it? Okay. And then look at the end here. What cancels? I'm going to work backwards. I see the -1 over n cancel with that 1 over n. I also see that this -1 over n minus 1 cancels with that one. So those two killed each other. Those two killed each other. What about this 1 over n minus 2? Would it go away? Yeah, because it should be canceled out with something from there. Shouldn't the one right before it should cancel that one out? And everything inside this ... should go away also, right? They should all be canceling each other out. The only thing that did not get killed off here was the one in the very beginning and this -1 over n plus 1 at the very end, right? Those two did not get killed off. So I'd like for us to write out in words the pattern of canceling that we saw here. And I know for this first example, you're going to be like, okay, why are you making this more complicated than it has to be? But trust me, for the next example, this is going to be helpful. Would you all agree that if you were trying to explain to somebody the type of canceling that was happening here, you could say this, and maybe you would say it a different way. This is the way I'm going to say it. I'm going to say the second number in a parentheses, I'm going to just be using very shorthand. The second number in a parenthesis cancels the first number in the parentheses 1 down. Okay, so what do I mean by that? If you go to any one of these parentheses, okay, go to any one of these parentheses and look at the second number. So here, I'm gonna go this -1/4. That second number in that parentheses will cancel with the first number in the parentheses 1 down, 1 to the right. So that should kill off the first one, 1 parentheses down. Does that make sense? Now you can also say this the other way around. You could say that the first number in a parentheses cancels the what?
Second number,
The second number where?
1 up.
In the parentheses, 1 up or 1 to the left. So I guess up means left and down means right, okay? You could say it either way, couldn't you? So if I look at, let's see, highlight here in blue again. If I looked at that first guy right here, the first number in this parentheses, it cancels with the second number in the parentheses 1 in front of it. So it canceled with that thing that was in there, right? Okay, good. Now, at the end of the day, here's what we have. What's S sub n? It's the two things that were left, 1, and then at the very end, we had the minus 1 over n plus 1. And now what we do is we take the limit as n goes to infinity of this nth partial sum. And of course, you know, if n goes to infinity, this thing goes to 0, and then you just get 1. So yes, the answer was 1. Which means if we were to add these numbers up forever and ever and ever and ever, it would get closer and closer and closer to 1. You must, on the test, include all of this. If you just do this line right here and just say the answer is 1, I'm going to not give you much, okay? I'll give you a little bit for doing the partial fractions, but this is important. And I'm going to illustrate why in another example. Now, where does this phrase, or we call these telescopic or collapsing series, right? That's what we call these. It comes from this idea, the collapsing comes from the idea of, I always think of a bridge, you know? So like if you had a bridge that spanned across something, you know, here's my little suspension bridge, right? Then if that bridge collapses, what's left, right? So if everything in the middle kind of falls into the water below, right? The only thing left is, you know, the two ends. And that's kind of what happens here. Everything in the middle just kind of collapsed away, and you were just left with the two ends. Okay, now that explains the word collapsing. It's also called telescopic because like old school telescopes were those telescopes that were like a cylinder inside a bigger cylinder, inside a bigger cylinder, inside a bigger cylinder. And so you would open the telescope up and look through it, and then you close it, right? Have you seen those? Yes. And so what happens is when you close it, you know, everything goes inside the previous one, and all you're left with is basically the two ends come together, right? So that's where the two names come from. I like collapsing more than telescopic personally, but there's, you know, whatever. Okay, let's look at another one. Ready? Find the sum. See, I just gave you a hint, didn't I? You know what? I'm going to not start this at 1. I'm going to start this at 3 to infinity. 1 over n squared minus 1. Now, there's a reason I didn't start it at 1. Do y'all see why I didn't start it at 1? What would happen if I try and plug 1 in here?
Be undefined.
Be undefined. So I started it at 3. Big deal, right? So we're going to start plugging in 3. Let's just start writing out what these look like. Let's just write it out. If we plug in 3, we get 1 over what? 3 squared is 9. 9 minus 1 is 8. We get 1/8. Plus, now we plug in 4. Plug in 4, we get 16 minus 1 is 1/15. Plus 1 over, let's see, plugging in 5 now, 25 minus 1 is 24. And then the next one would be 1 over 35. And the next one would be 1 over 48 plus ... Okay. Let's see, Yusuf? How you doing, Yusuf?
Hello, Professor.
Doing all right. I'm sorry, I know some of y'all have already like responded. I'm trying to keep track of y'all. But my question to you, sir, is what, if we're following kind of a procedure here, what would be the first thing you look at here?
I would look at that it's monotonic and it's decreasing.
Okay,
And then let's see. And then we would do
in
the
terms
partial
of
fraction.
series, right?
Sir.
What if we looking at like the formula sheet, right?
Mhm. Oh,
You start running through this, right? So first thing would be,
I would check if the nth term.
okay, so let's just do that real quick. We'll just do an nth term. This is the pregnancy test, right? So what is the thing we're going to take the limit of, Yusuf?
A sub n, which is 1 over n squared minus 1.
And where's that headed?
That is headed to 0.
0, okay. So what that means, Yusuf, is that you could still be pregnant. You might not be pregnant, but you still could be, right? Yes? So that test fails, okay? Fail test. All right, so now you'd say, is it geometric? So Yusuf, does this look geometric to you?
No, sir.
No, it doesn't, right? Geometric. And the big thing that tips people off about geometric is the n has to be up in an exponent, right? We don't have that, so it's not geometric. All right. Nth term didn't work. Harmonic?
No, sir. It's
Nope.
quadratic at the
That's
bottom.
right, quadratic on the bottom, okay. But, you know, I did tell you to find the sum, didn't I? And when I said that's a hint to you, so this should be leading you into the whole idea of telescopic, right?
Mhm.
So just like we did before, we should probably try some partial fractions, right, to break this up. Because when we look at this sum right now, the way it is, nothing cancels, does it? Like nothing is canceling. But if we rewrite it using partial fractions, we're actually gonna be able to see cancellation, hopefully. All right, good job, Yusuf. That's all I wanted. Let me do my partial fractions over here. We have to factor the denominator, don't we? Right, we have to factor the denominator. N squared minus 1 is difference of squares, so I factor it that way. It's going to give me an a over n plus 1 plus a b over n minus 1. And can I just save us the time on this and just give you what it is? Is that all right? So what you wind up getting here is -1/2 for a. And then for b, you get +1/2. All right, you all okay with this? All right, so this becomes sum n equals 3 to infinity of -1/2 over n plus 1 plus 1/2 over n minus 1. And the good thing is that one of these is positive and one is negative, right? Do y'all see that? So we should get some cancellation to happen. We'll see. But I think before I do anything, I'd like to just manipulate this a little bit. Let's see, how about I do this? -1 over 2n plus 2 plus 1 over 2n minus 2. Do y'all see what I did there? I just took those 2's and just dropped the 2's down and distributed them through. All right. Christopher Ver, are you here?
Yep, I'm here.
Okay. Can I split those up, Christopher? Can I split those into 2 different series?
Yes.
So what I'm asking is, can I do this? This was our partial fractions. So my question is, can I do one of these like this? And then plus the other one like this?
Yes.
Okay. You can only do that, Christopher, if these two both converge. Christopher, can you tell me just by looking at this one and looking at this one, what types of series these are individually?
Oh, they're both harmonics.
That's right. And that means they do what?
Diverge.
Okay, and if these diverge, then you're not allowed to split them, right?
Mm-hmm.
Yeah, so we can't do this. Again, this is something I see on tests. Students will do the partial fractions and they'll get to here and they'll split it and they'll say, oh, these are both harmonic, everything diverges. That's not what happens, okay? So just be careful on that, all right? So if we can't do this, then probably our best bet would be to start writing out, just listing out all the things, like plug in n equals 3, then 4, then 5, then 6, and see if we can find a pattern in the canceling. All right, I'm going to go through this. I'm still continuing here. Let's let n be 3. Remember, we're starting at 3, everyone, right? We're starting at 3. So let's see what happens when I plug in 3. Negative 1 over, what is that? 8 plus 1 over what? 4?
6. Oh, 4.
4, right? Then we have plus, now what's the next one? Be careful. Here we're plugging, that was n equals 3. Now plug in 4 for n. So we get negative 1 over 2 times 4 is 8 plus 2 is 10. And then plus 1 over, we're plugging in 4, 8, 6, 6, right? Boom. Yes? Did anything cancel in those? Nothing canceled. Okay, well, keep going. All right, now we plug in, where are we at? 4, 5, we're plugging in 5, so we should get negative 1 over 12. And then plus 1 over 8. Did anything cancel there? Ah, do y'all see that? Yeah, look at this. This negative 1/8 looks like it's going to cancel with that one, right? Let's keep going though before we get too far ahead of ourselves. Okay, now the next one will be negative 1 over 14 plus 1/10. Do we get that same pattern of canceling? We do, right? That one and that one are going to go away. Let's do maybe 1 or 2 more. Negative 1 over 16 plus 1 over 12. And then I'll do one more after that. Negative 1 over 18 plus 1 over 14. And we still get the same cancellation pattern. We've got this guy and this guy. We got this guy and that guy, right? So lots of things going away there, right? Lots of things going away. If you were to explain what's happening to me in words, does someone want to volunteer to explain to me in words what's happening? Kind of like I just did in that previous problem. Where's that previous problem? Like in words, I was trying to explain the canceling. Does someone want to explain to me how this canceling is happening? Anybody?
The first number in the first parentheses
Okay, hold on.
cancels
First
out.
number in a parentheses. Okay. What about it?
Cancels out the second number in the parentheses 2 down. Or
Yep.
3 down, wherever the
In the parentheses, 2 down. So not 1 down this time, 2 down. So let's just see if that works. That was Coleman, right? Okay, Coleman said that if I pick any first number in a parenthesis, so I'm just going to pick this one right here, that it should cancel with the second number 2 parentheses down. So if I go 2 parentheses down, that means boom, boom, here, I should look at the second number there and those two should be canceling each other. Yes, that works. And that works for every one of these, right? You can double check. Let me see, can somebody else give me that same sort of statement, but the other direction? Like if I force you to say the second number in a parentheses cancels, who wants to tell me how to finish this?
Cancels with the first number, in parentheses 2 up.
Yep, 2 up, right? So let's check that. If I pick a second number in parentheses, here we go. I'll pick pick 1/10. And I go 2 parentheses up and look at the first number, it cancels. Boom. Those cancel. Let me try that again. If I pick a second number in a parentheses, like 1/6, it should cancel with the first number 2 parentheses up. Uh-oh, right? It doesn't have a parentheses 2 up, which means nothing kills the 1/6 off, right? Nothing kills off the 1/4 either. So there are some things that are still here, right? There's some things that are still here. All right, so this is good. This is all just to try and establish the pattern. Now we have to come up with a formula for S sub n. Equals. So I'm going to rewrite everything again. Giving myself plenty of room. Students always ask me, like, how many of these should I write? And I always say, write enough of them to establish the pattern. Plus, then you say dot, dot, dot. And then way at the end, you need to put what the very last one would be. So that's the original formula with just n in it, right? -1 over 2n plus 2 plus 1 over 2n minus 2. That's what the formula looks like if I plug n in to this, right? The next one's going to be harder to see. Because what am I going to plug into the next one? Not n, but what? One less, right? And take away 1. So I've got to get this formula right here, and I've got to replace the n's with n minus 1s, right? So I'm going to do that down here, just like scratch work right below it. I'm going to go replace that n with n minus 1. Does everyone understand what I'm doing? I'm taking this original formula, I'm replacing the n's with n minus 1. Let me just see what that becomes. -1 over, I think that's just 2n, right? Just 2n, because it'll be 2n minus 2 plus 2. This one will be 2n minus 2 minus 2. That'll be 1 over 2n minus 4. Can anybody tell me what the next one's going to be without doing all the plugging in? Have y'all seen what the pattern is? Do y'all see what's happening with these numbers as you move? Look at the first numbers, all the ones that are negative. Do you see the denominators just keep on going up by 2? And do you see that same with the 1/4? It goes up to 1/6, then 1/8, then 1/10. So everything's just adding 2 each time. You can see it if you look at it backwards. This negative one, when we went backwards, we just subtracted 2. When we took this one, we just subtracted 2 from the bottom. So my next one should just be -1 over 2n. I need to take away 2. And then plus the next one should be 1 over 2n, and then take 2 more away, so -6. I think that should be enough for us to establish the pattern here. First guys cancel, second guys 2 down. This first guy cancels with the second guy 2 down, gone. First guy cancels with second guy 2 down, gone. How about this -12? Is that going to go away? Yeah, somewhere in here it's going to cancel. -14 should cancel with something in there. The only things that didn't cancel were the 1/4 and the 1/6. Now I'm going to do the same thing at the end. I'll ask you to look at this second guy here. Does that one cancel? Second guys, second numbers in a parenthesis cancels with first numbers 2 up. So 2 up from here, there it is. They're gone. How about this second guy right here? Second number, 1/2n minus 4. Go 2 up. Well, it's not there, but it's in there, right? It's somewhere in that ... That should go. This second one should go. The thing that doesn't go are these first ones, because those first ones need second numbers 2 down, and we don't have anything 2 down. So those stay. So everything in yellow stays. Everything else collapses, right? And we're left with 1/4 plus 1/6 minus 1/2n minus 1/2n plus 2. So I just took these that were negative and I just put the minuses out front. Any questions? What's next? Everything's collapsed, so limit time, right? Limit, and goes to infinity. Of that, I'm not going to rewrite it, but I think it's obvious that those two pieces go away, and you get 1/4 plus a 6th, which if you get a common denominator, 10/24, is it 5/12? 6, 4, 10/24. Yeah, I think it's 5/12. Converges to 5/12. What do you think? You have to show.
I have a question. It's I know you said like it might be obvious, but it wasn't. Why did the 1/2n and the 1/2n plus 2 cancel out? Like why did they go? Like I'm talking about an S sub n.
In S sub n, these two?
Yeah, it's like, but why did those two go? It's like when you were taking the limit.
Oh, okay, because I have, with both of those, you have a fixed number over something that's going to infinity on both of those, right? As n goes to infinity, those two go to 0. So that goes to 0, and then that goes to 0.
All right.
Yes?
Yeah.
Okay, so it converges. It converges to 5/12. All right, I have one more for you. I'm going to let you look at this one for a little while, then we'll talk about it. Sum n equals 1 to infinity. The natural log of n plus 1 over n plus 3. All right, I'm going to give you, let's take like 5 minutes. I'm going to let you just kind of go through, and I'll call on somebody to see how they approached it, and you won't be able to finish the problem, but at least get started, okay? And start it like you would, like, you know, here's a fresh series, where do you begin, right? Okay. So I already put up here kind of the process you should have gone through. You run the nth term test. So you take the limit of the sequence, and then you can do the limit of just the inside, and that's infinity over infinity. L'Hopital will give you a 1. So you're doing the natural log of 1, which is 0, which means that the test fails. Any questions there? It's not geometric because you don't have n up in a power. It's not harmonic because you definitely don't have a constant over linear. So we start writing out the sum, and we realize we don't see anything canceling, right? There's no minuses. So does anyone have any ideas? Because partial fractions won't work either. Ross, what do you got?
So what I did is I split the natural log up to where it was a natural log of n plus 1 minus the natural log of n plus 3.
So you're using properties of logs, right?
Yeah.
So you're using this property right here. If you have natural log of, let's say, x over y, property of log says that's natural log of x minus natural log of y. Division inside of a log becomes subtraction of 2 logs. So we can rewrite this as natural log of n plus 1 minus natural log of n plus 3. Good. That's it right there. That's what you have to be able to see on this. Once we rewrite it, now when we start writing out the sum, we'll get natural log of 2, minus natural log of 4, plus natural log of 3 minus natural log of 5, then plus natural log of 4 minus natural log of 6, plus natural log of 5 minus natural log of 7, and so on and so forth. That makes sense to everyone? Okay, now where's the canceling happening? Looks like I've got this one and that one. Looks like this one and that one. So let me call on somebody. Let's see, I called on Jane already. Peggy has answered. Ross has answered. Varun's answered. Nick, you around, Nick?
Yeah, I'm here.
Okay, Nick. So if you were to explain in words what the canceling, how the canceling is happening here, how would that look, or how would that sound?
Honestly, I'm not really getting that far along with this.
Okay. All right. So you see the negative natural log of 4 cancels with the natural log of 4, right? Those
Yeah.
two. Okay. So the negative natural log of 4 is the second number in this parentheses, right?
Mm-hmm.
Okay. So what we could say is that if you are a second number in a parentheses, you should cancel with the, well, look at this natural log of 4. Which number is that in this parentheses?
The first number in the third parentheses.
In the third, we'll say, we won't look at it as the third parentheses like in total. We'll just say that parentheses is 2 down from this one. So if this is the first parentheses, it's in the third one. So it's 2 down. That makes sense?
Yeah.
Okay, 2 down. Okay, good. The other way we could say it is that the first number in a parentheses cancels. So this is the same exact thing that happened before, right? With the second in the parentheses 2 up. Wasn't that the same pattern we had before? Like in the previous example, it was 2 down, 2 up. I gave my other class on Thursday. I gave them an example where the cancellation was 3 down. So it doesn't have to be 1 down or 2 down. It could be 3 down. It just, it depends. I wouldn't on a test go any further than 3 or 4 down. I mean, I wouldn't make it like 8 down or something like that. That would just be torture. All right, so let's see. Christian, I know you've answered, but I'll call on you. Christian, what should I do next?
We should rewrite, well, we should write the last term.
How do you mean?
So it would be the natural log of n.
Okay, yes, so you're telling me to do the right thing, but I want everyone to understand, we're actually at this point starting kind of over. And we're saying, okay, now that we know what the pattern is, let's find the formula for f sub n. Let's find the nth partial sum. And then we'll just redo all our canceling, make sure that we know what's left, what stays, and then we'll be good to go. We'll take the limit of that, right? So we have to rewrite everything now. So the first one's natural log of, first one's natural log of 2 minus natural log 4 plus natural log 3 minus natural log 5 plus natural log 4 minus natural log 6. That should be good. Plus dot, 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 plus. Now the one at the very end, Christian said, would be natural log of n plus 1 minus natural log of n plus 3. That's the very last one we would have. The one before that, I'm going to run out of room. What would the one before that be? Christian, you want to tell me what the one before that would be?
The natural log of n plus 2.
Is it?
Oh, I'm sorry, just n.
Just n, okay, because we're going to take one away, right? Okay, then minus natural log of
yeah, n plus 2.
N plus 2, there we go. So we're just subtracting 1 as we go back. And I'm going to have to squeeze one more in here. Natural log of n minus 1 minus natural log of n minus 3. Or sorry, plus 1. I don't know why I said that. And now we do our canceling. So I'm just going to start writing all the things that cancel. We've got the natural log, negative natural log of 4 cancels with that. Negative natural log of 5 cancels with something in there. Negative natural log of 6 cancels with something in there. The things that remain are natural log of 2 and natural log of 3. Those don't have anything to cancel with. And at the end of this partial sum, the natural log of n plus 1 cancels with the one 2 up. Natural log of n cancels with something 2 up. This natural log of n minus 1 cancels with something 2 up. And the only things that remain are this one and this one. The ones in yellow, the ones in green that I canceled by using this idea. That first numbers in a parentheses cancel with the second number 2 up. So, you know, for everything in yellow, I keep on saying yellow, for everything in green, there was something 2 up for it to cancel from. The reason why these, let me see, I'll circle them in gray there. Those two stayed because they're second numbers. And second numbers require first numbers 2 down or to the right, which I don't have 2 down. So those stayed. So my S sub n formula is natural log 2 plus natural log 3. Those are the yellows from the beginning. And then minus natural log of n plus 2 minus natural log of n plus 3. And now I take my limit as n goes to infinity of this. And what happens when I let n go to infinity here? What happens to this here? If n goes to infinity, natural log of infinity is, think about what the natural log function does as you go to infinity.
Infinity?
Goes to infinity. Yeah. So that right there is headed to negative infinity. because there was a negative in front. And then this one right here is also headed to negative infinity. And then, you know, up front, you just have natural log of 2 plus natural log of 3, but those are just numbers. So if you take two numbers and you subtract infinity, this thing goes to negative infinity, and that means that the original series diverges. See, it doesn't go to a number, it doesn't converge. That's the danger. That's the danger of not doing this step. If you don't do this step and you just look right up here at this line, you may be falsely under the impression that all you're left with is these two, and your answer is natural log of 2 plus natural log of 3. That is not correct. This diverges. The only way you see that is by writing out the nth partial sum, collapsing everything away, and seeing what you're left with, okay? Now, just to verify, I'm going to show you the first problem we did. It was 1 over n times n plus 1. Okay, that was it. Whoa, what's going on here? I don't know what's happening here. Let me try this again. 1 over n times n plus 1. Don't know. Get rid of some of this stuff here. Delete, 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 delete. Come on. There we go. Okay, let me see if, let me just make sure this is working. Okay, that's working. Okay, 1 over n times n plus 1. There we go. Okay, so this is the problem I'm showing you now was the first telescopic we looked at, which was this one here, 1 over n times n plus 1. We concluded that this, after we did everything, it converged to 1. So let's just verify that. Of course, as we look at the sequence itself, the sequence goes to 0. That was the pregnancy test, and so we know they're going to 0. But as we start adding them up over here, that sum should start to converge to 1. You see it? It's converging to 1, getting closer and closer to 1. Now the problem we just did just now was natural log. Log of n plus 1, what was it, n plus 1 over n plus 3. Okay. Where the heck is my, oh, they're negative numbers. Okay, I'm gonna have to do a pause, change it because it won't show up on my graph. There we go. Okay, so we did the pregnancy test and we saw that the sequence was going to 0, right? They were going to 0. But look at the sum. It's blowing up, right? No matter how far out I go, it just keeps getting bigger and bigger and bigger. Now it's negative, but I changed the function so it would show up here. But yeah, it's diverging. That makes sense? All right, so in summary, we have from 8.1 or 8.2, we have 3 types of series, right? Geometric, harmonic, telescopic. The only 2 series you know how to find the sum of are geometric and telescopic. And that's only if you can show they converge, right? And then the harmonic always diverge. So now what we do is we move on to the next section. I'm just introduce the idea, all right? The next section is titled the integral and comparison test. So these are two different tests. They're not the same test. If you look at your formula sheet, we have so far the Nth Term Test. We have what to do when we have a geometric series. And then we also know what to do when we have a harmonic series. This formula sheet never talks about telescopic or comparison. I mean, sorry, telescopic or collapsing. That's something you would have to just analyze the series and determine on your own. There's not a test for it. Now, what we're going to discuss now are the integral and comparison tests. These two tests are what 8.3 is about. And then we still have more tests right after that, but let's talk about the integral test. We'll do that one first. All right, we're just going to get started with it. So this is more just a basic idea. So let's say that, let's say we have a sequence. So we're doing integral here. Test. Okay, let's say that we're given a sequence. And I tell you a couple of things about this sequence. If the sequence is positive, which means that it only spits out positive numbers, okay? And the sequence is decreasing. So if you visualize what this sequence must look like, it's positive, so you always get positive dots out, right? But it's decreasing, which means that you have to be going down, 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 right? But you can never go past the x-axis, so to speak, because it's always positive, right? So it's bounded below, so to speak. This says that here's how the integral test is going to work. We're going to say this. We're going to say let f of x, we're going to say f of n equal a sub n on, we'll say, yeah, we'll just do that. Let f of n equal a sub n. Further, f of x is the sequence, but on the real numbers. Okay, so let me explain what's happening here. We're starting off with a sequence that's positive and decreasing. And what we're going to do is we're going to convert the sequence back into a function of x, where not only do we have the dots, we have all of the function, the curve that goes in between the dots. Okay, so we're looking at more than just the sequence of dots now. We're looking at the entire, everything in between, okay? And we say if that function f is continuous, means that it doesn't have any breaks in it, and integrable, integrable just means that we can integrate it. Then if the integral from 1 to infinity of the function converges, so does the infinite series. If the integral from 1 to infinity of f of x dx diverges, so does the series. Now, all of this is written on the formula sheet, all right? I just like to write it all down again. So why is this true? Why is it that if the integral converges, that the original series must converge? Let's try and analyze this with the graph. Let's say that we have a sequence, right? So that when you plug in 1, you get some number, and when you plug in 2, you get some number that's smaller plug in 3, you get some number that's even smaller. It's decreasing, right? And they're all positive. And if we keep doing this, right? Then if we look at the function right here, that goes forever, this integral represents the area underneath that curve, right? So if the area converges, that means that the area here is finite. Then the sum of the sequence, that means if you take each of these dots and look at it like as a height, like you're measuring something with a measuring tape, right? Whatever that height is, plus that height, plus that height, plus that height. If you measure all those heights and stack them on each other, that should also be finite. Because if the total area is finite, then like part of it should be finite also. Does that make sense? Now, it does not tell you what the answer is. Okay, so if this, let's say that this area, you do this integral. Do y'all notice also it has infinity, so it's an improper integral? Remember how we did improper integrals? We had to do a limit. But this is an improper integral. If we actually get a number as an answer here, like let's say we do this and we get the answer as 4. That does not mean that this series converges to 4. It just means that the series converges. That's all it tells you. Now, what's really nice about this is that if the integral diverges, right, it doesn't mean the test fails. It actually means that you can say that the series diverges also. So if this area becomes infinite, then the series does too, which is a little harder to show, but you're just going to take it on faith, all right? So let me now look at the formula sheet. And we have here the integral test. Say you're given a series, okay? We're going to look at the sequence as a function. Now, if we look at that function and we take the integral from 1 to infinity of that function, this series will converge as long as the integral converges, and the series will diverge if the integral diverges. Now, you have to be careful because the function that you get must be continuous, positive, decreasing, and integrable. That's everything I said the sequence had to be. Positive, decreasing, the function must be continuous and integrable. If all those things are okay, then we can use the test. So I don't have a lot of time, but I'm just going to show you a very quick example. Very quick example. Let's say we were trying to do this. Not X. Shit. I do that all the time. Okay, look at that right there. First, nth term test, the pregnancy test. If you do that, you're going to get an infinity over infinity. You do L'Hopital one time, you're going to get 0. The test is going to fail. It's not geometric. It's not harmonic. You can't do partial fractions because the denominator can't be factored, right? N squared plus 1 can't be factored. So you can't do partial fractions. So it's not going to be collapsing. So you're stuck. But you do realize that if you were to look at this as a function of x, 2x over x squared plus 1, that everyone in here would have no problem, I say that with confidence, that everyone in here would have no problem integrating that. Because it's just a basic u sub. U is x squared plus 1, the derivative of that's up top, right? So given enough time, you know, I'm confident that everyone here would realize the antiderivative of that is just natural log of x squared plus 1. And then you still have to evaluate it at the 2 endpoints, 1 and infinity, which would mean that we would have to do like an improper integral and take a limit. But just think about what would happen if you plug something that gets infinitely big into this. That's going to get infinitely big. And then if you plug in 1, you get a number. So essentially, this is going to become infinite. And so this series should do what?
Diverge.
Diverge, right? The integral diverged because it was infinite, so these series should diverge also. Now, this is not done because in order to run the integral test, you have to show, first of all, that that's continuous, integrable, positive, and decreasing. Okay, so I only have 10 seconds left. Is that a continuous function? Does it have any holes, any problems? There's nothing you can plug in that's going to make this undefined. Never will you get division by 0. So it's continuous. Is it integrable? Well, can you find the antiderivative of that? Yeah, okay, so it's integrable. Is it positive? Are you always going to get positive numbers out? Yes and no. As long as we're looking between 1 and infinity, then this is always positive, right? So that's all that matters. Is it decreasing? This is the harder one. How do we show that a function is decreasing? Cal 1. How do you show that something is decreasing in Cal 1? That's a drum roll.
Is it by checking concavity?
Close, not concavity. That's second derivative.
First derivative?
First derivative. To be decreasing means that your first derivative has to be less than 0, right? If your derivative is negative, you have a decreasing function. So what I would have to do to show this last thing is take the derivative of this and convince myself that it's always a negative number. How would you take derivative of that? Quotient rule, right? I'm going to do it 2. So I'm doing derivative of top times the bottom minus derivative of the bottom times the top all over the bottom squared. I'm going fast here because I'm out of time. That's the derivative of that function. If I clean this up, is that right? Yeah, if I clean this up, derivative of top is 2 times the bottom minus derivative of the bottom, which is 2x times the top. If I clean this up, let me see, 2, I would get 2 minus 2x squared on the top. On the bottom, I'm going to have x squared plus 1 squared. That's always going to be a positive number. So do y'all agree with me that this will always be negative? As long as I plug in numbers bigger than 1 for x, right? As x gets bigger, this thing will be negative. So this should be less than 0, you know, eventually. So my function should be going down. So that's what we're going to do next time. We're going to look at series where everything else that we have doesn't work. And then we're going to bring in the integral test. We'll have to show these 4 things, then do the integral, and then whatever happens is what happens to the original series. All right, everyone, that's it. Your test is due about 24 hours from now. Right, I'll be in my office hours today from 1 to 2 if you need me. All right, we'll come back and we'll hit more of 8.3 next time.
Thank you, sir.
All right, y'all have a great one. You too.